Consider two objects in the universe that exhibit a gravitational attraction between them. Well, the gravitational force exerted by object A on B is equal to the gravitational constant by the product of both masses over the squared distance between them. And to get this in vector form, we put a negative sign and multiply by the unit vector from object A to B. So as we can see, the force of A on B points against the unit vector, which is equal to the radial vector from A to B on its magnitude. And by Newton's third law, this is equal to the negative of the gravitational force exerted by object B on A. So as we can see, the gravitational force is proportional to the product of the masses and inversely proportional to the squared distance between them. So effectively, if we divide this force by the mass of object B, then what we get is a gravitational field of object A. Which effectively describes the gravitational acceleration at any point in that field. And this is convenient because we can place some mass, which we call the test mass, anywhere in a gravitational field, and you can simply multiply the gravitational acceleration by this mass to get the gravitational force exerted on this mass. Suppose we have an object placed on the surface of the Earth, which has a mass m. Therefore, the radial distance between the center of the Earth and this object is re. So using Newton's law of gravitation, the gravitational force exerted by the Earth on this object has a magnitude of the universal gravitational constant by the mass of the Earth and the mass of the object on the radius of the Earth squared. And by Newton's second law, that's equal to the mass by the gravitational acceleration. So therefore, if we cancel out m and substitute for the universal gravitational constant and the mass and radius of the Earth, and note that you should use the proper units, so if you multiply this by 10 cubed meters, then you'll obtain that the gravitational acceleration of the object is around 9.8 meters per second squared. And this is a really good approximation for objects that are close to the surface of the Earth. And when we've been using this acceleration, we simply just called it g. Suppose we have a mass m placed at some distance r from the center of a spherical body. So that means the entire mass of this spherical body will exert a gravitational force which has the following magnitude by Newton's law of gravitation for objects that are outside the sphere. Now what if the mass is placed inside the sphere? Well, in that case, only this part of the sphere is going to exert a gravitational force on the object. And the magnitude of the gravitational force exerted by this mass is as follows. Now the mass of that sphere is simply the density multiplied by that volume of that inner sphere, where the mass has a distance of r from the center. Now we can multiply this by the radius of the entire sphere cubed on r cubed. And we don't modify the expression, and therefore we notice that this here is equal to the mass of the entire sphere. And now we can substitute for m0 into this expression. And then doing some cancellations, we get the following expression. for objects that are placed inside the sphere. So therefore the variation of the gravitational force is linear for objects placed inside the sphere, and it drops off according to the square of the distance of the object when the object is outside the sphere. So effectively, when the objects are placed outside the sphere, the mass m behaves like a particle, with all the mass concentrated at the center of the sphere. A uniform rod exerts a gravitational force on a particle. And write the magnitude of this force in terms of the following variables. Well, if we take a differential element from the rod, it's at some distance x from the origin of the rod, then this differential mass element exerts a differential gravitational force as follows. And we can write the differential mass as the density by the cross-sectional area of the rod by the width of that element, and then dividing through by the mass, which is density by area by the length of the rod, which gives us the following expression. And now we can replace the differential mass and then integrate over the length of the rod to obtain a gravitational attraction produced by the entire rod on this particle. So by taking the constants outside the integral, we can write the gravitational force as follows. And I'll leave it for you to evaluate this integral using U substitution.